naught by kf. This one will be actually added up f by f naught square, and this one will be twice x f by f naught square by kf. This is equal to, this is sine square phi equal to, so this is x cosine phi. Okay.
Sir, excuse me, sir. Have you turned on the camera?
On.
Yeah, it is on.
It is on, right?
Okay, sorry, sir. Sorry. My bad, sir. Some issue at my end.
I think there would be some issue at your end. So yeah, the camera is on. Okay. So this is the equation of the curve, or of the radius of the curve in the xz plane. So what I have done, we have just eliminated t from this side, from both x and f, and got the curve. So t appeared as a parameter of equation of this particular curve. Now I have eliminated that curve. So now what curve does it generate, this equation? What would be the curve?
Sorry, ellipse.
Elliptic.
It will be ellipse. Okay. So you can check that with the usual technique. So if you write down this x, this was x prime, let us say x prime. So if you write down x divided by f naught by k, so x prime square plus f prime square minus 2 x prime f prime cosine phi. This is equal to sine square phi, where x prime equal to x divided by f naught by kf, and f prime equal to f divided by f naught. So this is the equation, because this you can check. This is the equation of an ellipse. Okay. Phi, you can check the this one, cosine square phi. So what is the check? What is the check for ellipticity? What is, whether the equation is ellipse or not? How to check that? Anyone can tell me? So how to check whether this hyperbola function, quadratic function, is ellipse, hyperbola, or parabola?
So that b square minus 4ac.
B square minus 4. So here b square will be equal to, well, here I have this form, so b square will be 4 cosine square phi minus 4 into 1 into 1. So that will be equal to minus 4 1 minus cosine square phi, which is equal to minus 4 sine square phi, and this is less than 0. So this becomes actually an equation of ellipse. You can find out the equation also in the standard form by just by changing the variable. So if you write down, let us say, if you take a different variable, so if instead of x prime and f prime over there, I possibly would otherwise. So f prime and x prime. Let us take another function. Let us say f double prime and x double prime. So with certain angle theta, so you can get that. So therefore, this becomes actually f double prime. So if we write down f prime as f double prime cosine theta minus x double prime sine theta, and x prime equal to f double prime cosine theta. This will be f double prime will be this x double prime sine theta, and this will be f double prime sine theta plus x double prime cosine theta. So what I am doing, I am changing the axis, I am tilting the axis, and then by selecting the value, suitable value of theta, just you can easily see that if you if you just do this calculation a little bit, then if you see the equation, you will find out a theta. And from this theta, you can get that this equation becomes actually a standard form. This one certain factor, so maybe a square plus f double dash square by b square. This becomes equal to 1. So this is in the standard form you get. I'm not doing this exercise. You can do that exercise itself. But what you see for this equation, actually, it becomes so f and x. So if you draw this becomes like an equation tilted ellipse. Okay, tilted ellipse. Now what will happen? So what happens? Let us say when we have zeta equal to 0, there is no damping. X and f. So f equal to f naught cosine omega t, and there x will be equal to f naught by k. So f naught by k, and this one is 1 minus r square. 1 minus r square modulus, and this will be equal to cosine omega t. You see that when zeta is equal to 0, so it will be x by f will be one function a. So this will be actually x by f will be equal to 1 divided by k 1 minus r square. Okay, more of that. So you see that this becomes a straight line. Okay, when zeta equal to 0. As zeta increases, so therefore this becomes 0. As zeta increases, what happens? At zeta increases, then this function actually this is 0, because while going up and coming down, if you increase the value, so when the t is increasing or decreasing, it is following the same straight line, so that there is no area enclosed by this curve. So this is a straight line, so therefore the area under the area enclosed by the curve will be 0, and that actually corresponds to what we know, because when the value of damping is 0, then there is no net dissipation of energy per cycle. Whatever comes out from the source in one point of time, it comes back to the again to the source at some other portion of the cycle. So there is no net loss of energy from the system. Okay. Net loss of energy means that the energy of the total energy of the systems remains constant for every cycle. So it does not change. So there is no need of getting any energy from the source. Okay. So that is what we have. Now, if you increase the value of zeta, what you get this one like that. Okay. Now you see one thing. That this equation, let me just write down this equation. So x square divided by f naught k by f naught by kf kf square plus f square divided by f naught square minus twice x f divided by f naught by k f naught square kf. This is cosine phi, that is equal to sine square phi. Now what we see here is that this becomes, now let me look at this point. Okay, so the maximum value of the force that happens at certain time. So this is the, when this happens, F max. And what is the value of F max? This F max will be equal to F naught. This is equal to F naught. Okay, F max is F naught. Okay. And at this point of time, and so at certain point of time, F becomes equal to F max. But now see, X does not becomes X max. So X max is this value, X max. Because F equal to, if F is F naught cosine omega t, X equal to X naught cosine omega t minus phi. So what happens that at this point, so when this is maximum, let us say this becomes omega t equal to 0, let us say at one point of time, t equal to 0, f equal to f naught, this is the maximum value, but here that becomes x naught cosine phi, x max cosine phi. So this is less than x max. So at this point, this is less than x max. Similarly, when x max equal to 0, this becomes actually, so here at one point of time, f is here and f is x max, but x is less than x max. But at another point of time, let us say when f becomes 0, okay, when f becomes 0, then x will have certain value, and this value is positive. Well, when f becomes 0, that means this is the part. X will have, when f becomes 0, then x will have either these two value, x equal to f naught cosine phi, since sine phi is actually positive quantity. So here what you see is that at this point, this is the point here at a different point, which is at f equal to 0, this is like that. So what we see from here is that the curve is actually traced in the this direction. Okay, so f is maximum, the value of f is maximum, then it is decreasing. So f is maximum, x is decreasing, and here f is here. Let us say when x is x max. So what I want to say is this one. So there is a phase lag. So maximum time when the f reaches maximum, x does not reach. It reaches maximum a little time later. So that means when f reaches maximum, so when f reaches maximum, no. Or just say when f reaches 0, x has certain value. When f reaches 0, that means cosine omega t is 0, x becomes actually, when f, so omega t equal to pi, let us say pi by 2, then this becomes actually, so omega t equal to pi by 2, so x becomes x naught cosine pi by 2 minus phi, so therefore x naught sine phi, and which is greater than 0. So when f becomes 0, here x is this part here, right? Now when x becomes 0, that is omega t, when so it is here, and when f becomes 0, when x becomes 0, then omega t will be equal to phi, x equal to 0. That happens omega t equal to phi plus pi by 2. So therefore f will be equal to f naught cosine phi plus pi by 2, which is equal to minus f naught sine phi. So when x equal to 0, x becomes 0. At this point, f becomes negative 1, right? So here the curve is like this. So this happens at one point of time when f equal to 0. This is the case when x equal to 0, f becomes actually negative 1. So the curve is traversed in this particular direction. So you see that at f is actually it is becoming 0, and then it is becoming negative. So if I write down f is a function, so at one point of time, at time this is equal to t, where f is equal to 0, I am plotting ft versus t. F equal to 0, this is cosine curve, so therefore at this point f equal to 0, which corresponds to this, and the other point x equal to 0, which has a, so f minimum, which comes over here, so therefore at a later point of time. So actually what you see from here, the curve is traversed in this particular direction. The area under this curve is equal to area under this curve, as we have seen that this is nothing but x dot square, cx squared dt, which is nothing but c, and x squared is equal to f naught by k square, and then omega square f square omega square, and this is equal to over the integral 2 pi by omega, so therefore this will be equal to pi by omega. So c f naught by k square f square omega times pi. So that will be the area under this curve. So what we now see is this one. At different frequency, because f is also a function of omega, so therefore at different frequency the area of the curve will change. Okay, area of the curve will change. So that means that this curve will actually also change in its size, because at different frequency the area will also change. But what we notice also that when let us say when omega, one thing of importance is that when omega is less than omega n, that means r is less than 1, then what happens? If the curve is in this orientation, so what happens is that the curve equation is suppose x prime square plus f prime square minus twice x prime cosine phi, this is equal to sine square phi, and suppose this is phi is 0 to between 0 to 90 degree. If you remember that the curve here if you just remember that 0 to pi by 2, the phi is like this, r equal to 1, so curve is like that. So between 0 to r equal to 1, what we have, phi is less than pi by 2. Okay, so this term is positive quantity. So this is actually this is x equal to, so this is a curve when you have so this function is positive. Now as soon as r is actually crosses 1, then this becomes actually negative, because this cosine phi becomes more than pi by 2. You see that this is after it crosses the r equal to 1 line, then phi becomes more than pi by 2, and this is actually becomes negative quantity. So then actually what happens that this curve will, suppose this is a curve which is obtained when r is less than 1. So what will happen when we get r is greater than 1 is that the curve will be like this when the r is greater than 1. So the curve will be actually flipped from this first and this quadrant to the other quadrant. Now what will happen to what is happening to the response? That means what is happening there? There is an abrupt change. So in the resonance there is an abrupt change, but for undamped damped system, this is not change is not abrupt. But what we see is that the phase difference actually going from 0 to pi, and there is a crossing of phase. This is crossing of pi by 2 line, and as soon as it crosses pi by 2, what will happen? The orientation of the curve will flip. Okay. So this is one important observation which can be used to detect whether the resonance is taking place or not. So what we'll do, normally in the experiment, suppose you want to find out the natural frequency of the system. So how to get the natural frequencies of the system? One is that you record the response of the free vibration. So if you let the system vibrate freely, then you can get that. But this way you may not be able to find out the frequency, natural frequency correctly, because what will happen, that response, so if it is free vibration you have, then the response will have the frequency what you get will be omega d, which is equal to omega n. So you cannot get the natural frequency from measuring the response during natural vibration, because in the natural vibration what will happen, the mass will vibrate with the frequency omega d, not equal to omega n, but it will vibrate with omega d. If the damping is very small, then we can neglect this part. Otherwise, if the damping is not appreciably small, then omega d will get, but it will not get omega n. One test to check the resonance is that what we'll do, we'll have this system. Then this is the forcing force, and that is the response I get. So what I do is that I take this to two terminals of, let us say, cathode ray oscilloscope or cathode ray tube, give this as one. So what you get is that you will see in the cathode ray tube, so what will happen at the two terminals, so cathode ray tube is an electronic element where at the two terminals you give two different voltages. Now if you give the voltages proportional to xt at one terminal and x proportional to f as another terminal, so what you get in the cathode ray tube the response something like this. So what we will do, we feed it to the cathode ray tube and see the response. So there will be an ellipse will be formed. You will see an ellipse. This ellipse, if you increase the frequency, so now what we'll do, we will change the frequency a little bit. So I increase the frequency from 0 I increase. So what we'll see that the area under, because the dissipation will be more and more, so the area under the curve will increase, and also it still will be also increasing to some extent. But as soon as you get omega equal to omega n, just before this part, you'll get the ellipse in this direction. When you cross omega greater than omega n, you'll see that the ellipse has flipped its orientation. So this may be a test to find out the resonating frequency, or omega n, the natural frequency. So in the natural frequency, so in the cathode ray tube, you will just see a flip of the ellipse to the other quadrant. So that is a shear testing of the resonance, or shear testing that the natural frequency is crossed. So if you just fiddle around with this cathode, with the signal generator, which will give you the frequency, with which you can change the frequency, you should be able to find out omega n fairly accurately. So this is one experimental way to find out the natural frequency of a system. Natural frequency can be found out by free vibration response, but that may not be accurate, where this one is quite accurate. Now, the hysteresis loop, which I was talking of all the time, that is the f and x. So this kind of curve like this. F and x. So now, in most of the, if you have a damper, which is actually a linear damper, you will get ellipse. But when you do experiment, you may not get very good ellipse like that. So you may get ellipse, something like a shape like that, or most of the time what you get that shape, something like that. So now that means that this damping there present is not a viscous damping. Most of the mechanical system will also have, in addition to the viscous damping, which is due to mainly the lubrication or the oil put into the system, but appreciable part of dissipation will come from dry friction. And dry friction damping is not actually will not give, if you have a system with a dry friction or the Coulomb damping, you will not get an ellipse. But if you get for the dry friction, you will get a something like this. Okay, so in the dry friction, you will get that. Now, in most of the cases, you will not get purely as a dry friction or a viscous damping, but you will get a mixture kind of thing. You will get normally you will get something like this form. Now, one way to model the, suppose you have done experiment and you have found out that fx curve is like that. Now, one way to model the damping is that we find, so no amount of viscous damping will be able to capture this part. But during modeling, actually, when we do not know about the damping, one way to model it like a viscous damping, but the viscous damping coefficient of the damping in such a way that the energy dissipation per cycle is exactly same as that of the original system. So what we do, we want to find out what will be the value of the equivalent damping. So C equivalent, we do not know. I know that there is no value of C which will give, so there does not exist any value C which will give us the curve as we have shown. But we can always find out an equivalent damping, which is, of course, which will not give the curve in same shape, but the area under this curve, this will be equated. So what we can see that we find, so area under this curve, which is the energy dissipation, heat dissipation, and this I have found out this will be equal to C x dot square. So if it is equivalent damping, what I am doing is that if it is an exact linear damping, then this is like this 2 pi by omega, and this becomes equal to C x naught square omega pi. If you calculate this integral, you will get C x naught square omega pi, where x equal to x naught cosine omega t minus pi. Okay, so you'll get that one. Now, what we do here is that we know what is the x max. Okay. Now, what we do, we find out, just my objective is to find out that amount of damping, C, which will give you the same area. So what we do is that we do the experiment, we find out we measure the hysteresis, we find out all the points on the fx plane, just by, as I have shown, I have told you, just feeding it into the two terminals of the cathode ray tube. We can find out this shape, and then we can find out this area under this curve. We can find out the area under this curve. Suppose the area is known. Suppose I know this area delta, let us say. So I know the area. Now what we'll do, we find out, so delta I'll equate to the C eq x naught square omega pi. So that is one thing which will give you the equivalent damping. Of course, this is not a linear damping, so therefore we do not expect nonlinear. We do not expect that C equivalent will be a constant function, but it will depend upon the amplitude. So equivalent, C equivalent depends upon the amplitude of the response, as you are seeing there. It depends upon the amplitude of the response. So this is what is very important, because in many systems where we do not know what is the exact nature of the damping, we can approximate this as a linear damping, and this coefficient of the damping, then we take this as an equivalent value. So equivalent linear damping we consider when the damping is not exactly a linear damping. We just find out what is the equivalent viscous damping, which will give you the same energy dissipation. Is this clear? Energy dissipation?
Yes,
Okay.
sir.
So equivalent damping gives the same energy dissipation. Okay. So now we have seen then xt. So now we have a damper. So this is actually forcing is present. Now let me summarize Ft, which is equal to F naught cosine omega t. And we have here the so what we'll get from this value is okay. Let us say we have the F naught all right. So xt will be equal to F naught by K times F, which is equal to 1 by 1 minus R square 2 zeta R square, and this one will be equal to cosine omega t minus 5. That this will be okay. Where xt equal ft equal to if not cosine omega t. All right. Now the energy dissipation, as I said that E dissipation, energy dissipation, this will be equal to C x naught square times omega times pi. Energy dissipation is like that. So now you see, this is the overall energy dissipation. So energy dissipation, which is a now function of omega, is like this. Okay. So energy dissipation. So now what we find out is energy dissipation, the dissipation at omega equal to omega n. Omega equal to omega n means that this will be R equal to 1. So if you put R equal, so this means that R equal to 1. So at R equal to 1, so xt, so therefore energy dissipation will be C x naught square, which is equal to F naught square by K square times this value, that will be equal to, what will that, 1 by 2 zeta R, right? C will be equal to, this is x naught square, so therefore this will be equal to 1 by 4 zeta square, 1 by 4 zeta square, and 4 zeta square, because I have to take the square of this part, so that R equal to 1, so this is 4 zeta square, omega equal to omega n, because R equal to 1, that is omega equal to omega n pi. Okay, so that is the energy dissipation per cycle. So let me write it down fairly. So this is energy dissipation. This is equal to then C. What will happen? C equal to 2. C equal to what? 2 zeta. C, I know that C is equal to 2 zeta omega n times C by m will be equal to 2 zeta omega n. So therefore C times m. Yes?
Yes, sir, that M was missing.
M is there. and this is f naught square by k square, and then 4 zeta square, then omega n, so omega n square. Okay, this one times pi. So that is what we have over there. Now, so this is the energy dissipation. So energy dissipation will be now 1 by 2 zeta, 1 by 2 zeta. So m by k will be cancelled out. So therefore f naught square divided by k times pi. I hope I have done it correctly. So this is the f naught square by that one, right? Yes. So this is energy dissipation at r equal to 1, exactly at resonance. Okay. Now, if you consider the energy stored, now what is energy stored? Suppose we have the so the energy. So what is happening? The spring will have. So this will be half. So the energy of the system is half mx double dot square, half k x square. So the maximum energy, see, at one point of time, what will happen? So this is the overall energy. So overall energy at different point of time. So the maximum energy, so x is actually this form. So if this is the response at the steady state, then these will actually alternate and the total energy will be constant. So the maximum amount of energy, so E maximum or E energy in that case is equal to, because this energy and that energy will be equal. So what will happen? Kinetic energy and the potential energy, these two will be equal, and because this is actually curve is like that, I should not say equal, but we can do that. So this is the energy. Suppose I consider that in omega n square, and x dot will be equal to x naught square cosine square omega t, omega n t, minus 5, okay, plus half k x naught square, okay, k x naught square, and so this will be sine, I think, x naught square, so therefore sine square, this will be cosine square omega n t minus 5, because I am assuming the response x equal to x naught cosine omega t minus omega n t minus 5. So that is it, and you see that m omega naught square is nothing but k square, so therefore this becomes equal to half. So this and these two are, so half sine square phi and here cosine square, so this will actually becomes. So this is the energy, total energy stored within the system. Okay, total energy stored within the system, that is this one. So this is the average energy which is stored, and over and above certain energy is getting fluctuated. So sometimes energy is coming in and sometimes is going out. So the energy of the system is actually is a constant value. This is half k x naught square, and x naught square is nothing but half k. So at omega equal to omega n, so therefore this becomes actually f naught square by k square and f square. And at omega equal to omega n, the f square value will be equal to 1 by 4 zeta square. Okay, 4 zeta square. One by 4 zeta square. Okay. Now, if you consider then, so E dissipation is like that, and E amount of energy stored is half kx square, like that. So the energy, so this is also the, see the maximum energy. So it is at the maximum point where there is no velocity. So at the extreme end, what is the maximum energy stored there? And this is equal to the energy which is actually energy which is constant over time. So you can either find out this way or that way the total energy of the system. Now, if you consider, please remember energy dissipation, please, just like that. So energy dissipation. So now I write down this one as energy dissipation divided by E. This becomes equal to F naught square. So that part will be there. So this is equal to energy dissipation, that will be energy dissipation per energy. So that will be what? This is pi F naught square will cancel out, half. So therefore 4 times zeta times pi. Is this correct? Can you check?
Yes, sir.
Huh?
Yes,
Yes.
sir.
Okay. So 2 pi times 2 zeta. Okay, 2 pi times 2 zeta. Now this part actually, now E divided by energy dissipation at R equal to 1. Okay. Times 2 pi energy by energy dissipation. Wait, so therefore E 2 pi E by delta, E by energy dissipation 1 by this. This is actually, this is 1 by 2 zeta. And this term actually 2 pi times, so what we can do is that 2 pi, if this is correct, 2 pi times energy present or stored in the system divided by energy dissipated per cycle. This thing, this has a name. Can you tell me what is the name of this quantity what we have written? 2 pi times energy stored in system divided by energy dissipated per cycle. This has the name as the quality factor. Quality factor of resonance. Quality factor of resonance. So this is equal to quality factor of resonance or Q factor of resonance. So quality factor of resonance for, this is defined for any system. That need not be a linear system, any nonlinear system, any kind of system. If I calculate the energy which is energy stored in the system, so this energy stored in the system remains constant for harmonic motion. Otherwise the energy, so what it's made by this, and when the motion is in the steady state, what is the average energy which is stored in this system? So this average energy you can find out, and this average energy stored in the system divided by the energy dissipation per cycle multiplied by a factor 2 pi. This is called the quality factor of resonance. So this is the quality factor. The quality factor is, you see that for the linear system, this is 1 by 2 zeta. So is that when the zeta is very small, then quality factor may be very large. So the quality factor actually denotes to some extent the sharpness of the peak in the frequency response function. Is this clear to you? The quality factor is very important in mechanical, in any vibration literature. The quality factor is mostly used in electrical systems, but in mechanical systems also it is quite important. So, have you understood the quality factor? Clear to you? Quality
Yes.
factor of resonance? Yes. So please remember this part, the quality factor, because oftentimes in interviews and so on, you are asked that what is the quality factor. Please do not forget this part. The energy stored in system divided by energy dissipated per cycle times 2 pi. Now let us look at this quality factor in a little bit more detail. So we have there. Now what I was showing that F is the magnification factor. Magnification factor, and this is equal to 1 by under root 1 minus r square 2 zeta r square. Right? Now, if we plot, so this exercise we did earlier, if we look near about the resonance, so assuming that zeta is very small, so near about resonance when r is approximately equal to 1, that means I am considering r equal to 1 plus epsilon, where epsilon is very small quantity. Such that epsilon square, etc., epsilon square, epsilon cube, all these terms are neglected. All these terms are neglected. So this is very small quantity. Now in that case, you can find out F square. So F will be equal to 1 divided by under root 1 minus r square. You see that r square will be equal to 1 plus twice epsilon plus epsilon square. So I neglect this part. So it becomes 1 minus r square will be equal to 4 epsilon. This is 4 epsilon square. Right? Similarly, 4 zeta square. So other term will be 4 zeta square r square and again you put r square equal to 1 plus 2 epsilon epsilon square. Now you see zeta is itself very small quantity. So I also say that zeta is actually also very small. So zeta square times epsilon will be again for the small quantity. So if you neglect that part, so therefore this r square, so if I write down here 1 plus 2 epsilon plus epsilon square and so on, this could be neglected. And we see now here 1 by 2 pi, 1 by 2 under root square plus zeta square. Okay. So now you see one thing from here, that energy dissipation. C. So energy dissipation will be equal to delta energy dissipation. That will be equal to, this is equal to C, okay, C x naught square omega pi, okay, and this part will be equal to C, that is 2 zeta omega n times m. X naught square equal to f naught square by k square times omega n times pi. All right. So this becomes equal to, so energy dissipation here f naught square by, so if I write down omega by omega n, so this becomes omega n square. So omega n square m and k, so this one will cancel with 1k. So you'll get f square by k times 2 zeta times r times pi. Now, one thing you see from this curve, so this will be f square and f square will be there. So I'm sorry, so this will be f square term will be there. Okay. Now, if you plot this f square, so f square, you see that now in the epsilon plane, the f square is like this, f square is like that. And one thing one can see that, so epsilon, suppose this is a curve drawn in the epsilon, okay, epsilon plane. So epsilon, if you integrate minus infinity to infinity, f square d epsilon, you see one thing that this becomes equal to, so this becomes equal to minus infinity to infinity, so epsilon here, this will be 1 by 4 epsilon square plus zeta square, and d epsilon like this. Okay, so this integration will be like that, and then this becomes equal to what will happen to this? This will be, what is the integration? Half. What is this integration from here?
Tan inverse.
Tan inverse epsilon by zeta, right?
Yes, sir.
Epsilon by zeta or epsilon?
There will be one more theta term outside.
Huh? Yes, 1 by
There will be one more theta.
1 by zeta, right?
Yes, sir.
Uh, one more zeta term. So 1 by x square plus x square. I have just forgotten dx. What is that?
1 by a tan inverse x by a.
X equal to a tan theta. So yes, are you sure 1 by a will be there?
Yes, sir. A will be there.
X equal to a tan theta, let us say. So therefore, this becomes this is a tan theta divided by dx equal to a sec square theta, a sec square theta divided by a sec square theta, yes, 1 by a. So this becomes actually 1 by zeta, this part. Okay. Now this becomes equal to, you see that this is 1 by 2 zeta. Okay, so energy dissipation, it's 2 zeta r equal to 1 plus epsilon, r equal to 1 plus epsilon. Okay, let me put not f square, but okay, f square will do our rule. Well, this you can check that this will be equal to 1 by tan epsilon, this one in 0 to infinity, and this becomes actually pi by 2. Pi by 2 times 1 by 2 zeta, because tan inverse infinity is pi by 2 and tan inverse zeta 0 is equal to 0. So pi by 2, 1 by 2 zeta. But what I am just looking at is the energy dissipation. So f square curve will have like that. But the energy dissipation part, just let me redo this exercise because the need is that energy dissipation, E dissipation, this is equal to F square. F square will be equal to 1 by 4 epsilon square zeta square, right? And this becomes 2 zeta, so this is 2 zeta times F naught square by K times R, which is equal to 1 plus epsilon pi. So energy dissipation, so if I do this energy dissipation, we can find this energy dissipation curve. That means now what I am finding out that if you draw this energy dissipation curve, then you see that if you integrate with respect to epsilon as I am doing that, suppose we get this energy dissipation curve like this, something like this. I integrate from minus infinity to infinity in the epsilon. What I am doing actually, I have inflated the curve and then taking from minus infinity to infinity, just show that when epsilon tends to infinity, actually R becomes appreciably less than 1, and then the function drops down to a very small value. So the effect of this part, this neglecting is actually an approximation. So I'm approximately calculating the this dissipation curve over the frequency. Now if you calculate that, then you see that epsilon by epsilon square plus zeta square d epsilon minus infinity to infinity. Because this is actually odd function, so this will be 0. Right? So this integral will be 0. Only this integral will come. So therefore, if you take the energy dissipation, d energy dissipation, d epsilon, so if you integrate over the whole thing, then you will get this part as 1 by 2 zeta was appearing there. So therefore, this becomes actually 2 zeta divided by 4 f naught square by k and pi, and then if you integrate, this will be equal to 1 by zeta and pi by 2. Okay, so 1 by zeta and pi by 2. So therefore, it will be equal to 1 by 4. So this particular value will be equal to 1 by 4 f naught square, zeta will cancel out, f naught square by k times pi square. So energy dissipation integral d epsilon will give you this value. Okay. So what I see here, that this integral is actually this area under this curve, energy dissipation over this one, this is actually independent of zeta. So that is one observation. But what we have seen that as the value of zeta increases, this becomes actually flatter and flatter. But the area remains constant. So what the possibility of this one is this, that when zeta is small, energy dissipation is like that. When zeta increases like this, further increases like this, such a way that the energy under this integral, under this curve from minus infinity to infinity, that actually becomes constant value. So now what we see that as the value of zeta is decreasing, so the peak is becoming sharper and sharper. And the quality factor, which is equal to 1 by 2 zeta, is actually increasing. So as the damping value decreases, so what we get, this energy dissipation curve, this becomes actually very sharp value. So at r equal to 1, you will get the maximum dissipation. Very close to r equal to 1, the energy dissipation will be very small. Okay, so for a low damping, but if you have a high damping, then over a larger bandwidth, you will get appreciable energy dissipation. So this is what we have observed from mathematics, and this is quite also clear from our physical institution, because the frequency response function is like this, f is like that. So if damping is very small, then this becomes actually large peak. So the energy dissipation, which is proportional to f square, so this actually becomes very small, just when you go a little away from the natural frequency. So the resonance condition for the low damping system at resonance, that is at omega equal to omega n, excitation frequency is equal to omega n, the energy dissipation becomes maximum. Okay, and it falls off very fast for low damping system, but for the high damping system actually it is appreciably slow. So therefore the energy dissipation will be quite large if the damping is large over a larger bandwidth. Okay. But for the small damping system, it is only during the resonance that energy dissipation will be very large. Otherwise, away from the resonance condition, the energy dissipation will be appreciably small. I do not want to go any further today because we do not have anything left, I think, in this single graph system, excepting solving certain problem. But if you have not understood anything so far in today's class, then you may ask me. But quality factor is very, very important concept in mechanical vibration that I am repeatedly telling you. Okay. Quality factor, you must know what is the quality factor, and quality factor is associated with the sharpness of the peak of the response frequency, the frequency response function of the system. Is there any doubt? Anything which you have not understood? Okay, most of this was there was some mathematical part which you will have to redo just to understand it, but the physical concept should have been clear by now. What does it mean by quality factor? How the energy dissipation is related to the hysteresis loop, the area under this curve of the hysteresis, and so on. So these are the physical, the concept of it, that should be clear. Mathematical part, I suggest you redo at your home. But apart from that, any other doubt? Okay, if not, then let us not extend today's class any further. Yeah.
So like in the previous analysis, you have assumed epsilon to be very small, right?
Yes, here also I am assuming epsilon to be
Then like how did you integrate using the same expression?
Yes, I am integrating from minus infinity to plus infinity. Actually, what is the reason behind that is that we are more or less considering, now this is one approximation which we do, we forget actually what this was also approximation. So, now I consider this is value less than 1, but I am integrating from minus infinity to plus infinity. So there is definitely a mismatch. I cannot approximate epsilon, this value, this epsilon is very small, as well as I cannot integrate, I cannot take this value epsilon to be very large. So that is possible when the integrand is actually falling off very fast when epsilon is going a little bit more than 0. So therefore epsilon, when it increases to 0, so I assume that this function is dropping very fast. So this is the assumption. This is true for low damp, small damp system, but then I cannot go it for a very large damping system. So I am considering with a very small damping, but what will happen when we increase the damping? Even if the increased damping remains very small. So in that case, the curve will be like that, like this. But at the same time, I have to remember that this curve is falling off very fast. So I have drawn it like this, but what we understand that I am considering all the integral here, this thing, where the function is dropping very fast. Otherwise, we cannot assume both. We cannot assume this, and we cannot integrate 0 to infinity with the same function. But the same function, if you draw the function 1 by epsilon square plus zeta square, okay, this function actually drops down very fast. So it is not, if this is zeta is very large, then this function, this is so large that this function will drop down quite fast if you go away from 0. Okay. Because the rate of decrease you can find out the epsilon of 1 by square zeta square. So this becomes equal to 2 zeta. So this is 2 epsilon divided by epsilon square plus zeta square. So this drops down very fast as well. Okay. So that's the thing. It is actually approximation just to give an idea. In physics, we make such kind of approximation. Of course, if you ask me that this is not rigorously mathematically correct, I admit that this is not mathematically correct thing, but this is just an approximation just to show you the effect of the damping. Okay, is this clear to you? It's just an approximation. Okay, it's
So,
not, you cannot, yeah.
So again, that integral like delta E dissipation into d epsilon, like what does it physically represent? Sir?
Oh, that is, it does not represent physically anything because this is energy dissipation. What I'm just trying to establish that energy dissipation, if you put energy dissipation, so in that approximation, energy dissipation curve is like this, epsilon, this is 0. So area under this curve, it does not represent anything physical. But what you can see that, well, I should not say that it does not represent anything, okay, because if you consider a function, any function, fx, its Fourier integral f omega, okay, let's suppose a real Fourier integral. So f square dx is equal to f star d omega divided by 1 by 2 pi. So this is a theorem known as a Parsifal's theorem, Parsifal's identity. So what it means, maybe time will be more appropriate. So the area under this curve, the T, is nothing but area under that one. So it does not signify anything physically, but what it shows that over time, the energy, so this is actually this kind of a power spectral density, which I should not want to go into those details things, but something like that, the energy, the total in any signal, any physical signal, the total energy content within the signal. This is something, a new concept. I do not want to go into that detail. But apart from that, looking so far what we have studied, it does not have, this integral does not have any physical significance. Yes, but if you look in a little bit more details, then you can get certain significance in terms of the the energy density function, which is something topic which is beyond this science. But well, I admit that there is no physical significance.
So,
Yeah.
so which book we can follow for these topics, sir? Because we cannot find this in the Mairovich book, sir, or SS Rao.
You may not get in any book, so that is thing. You may not get in any book. Okay, I'll give you some. I'll try to give you some handout, which I need to prepare, of course. So if you follow the books, then you will see that I am in fact not teaching from any book. But this particular thing, I should give you some write-up, otherwise you will not follow. You may look at any of the physics book, like Landau and Lipschitz mechanics. This has a number of volumes. Theoretical physics, I think that first volume, mechanics, it gives a little exposition to this kind of analysis which I have done. just you look at any of the physics book on oscillation, because mostly this is dealt in physics, the resonance and then peak, all this stuff. Mechanical engineering, of course, it is very important. Quality factor, it must be there in S.S. Rao's book. Is it not there?
So I did not check, sir. I have to check it today, sir.
Please check and let me know. Then I can give you some documents to read from. Okay, I'll give you. Maybe I'll take a photocopy of some material which I should look for, and then I'll give it to you. But let us look at the book and see what is there. Next class, you tell me what is there and what is not there in from whatever I have taught. Okay.
Okay, sir.
But I hope you are understanding it in the class, right?
Yes, sir, yes.
Okay, so that is needed. It is being recorded, I see, and you can look at the recording again. But make sure you understand what I am saying. Mathematics you redo, but physical concept should be actually made clear. It is this is very important to have a good sound physical concept of what is going on. Mathematics will be actually secondary, but physics is actually the primary part of this kind of syllabus.